to the next session on ANSYS CFD tutorials. In this session, we will analyze the NACA2414 airfoil for a different angle of attack using fluid flow fluent analysis. We will first go to fluid flow fluent and double click. Next, I'll go to geometry and right click. I'll import the geometry of 2414 airfoil. Then I'll double click on geometry. I'll make some changes to this airfoil. I'll go to extrude and I'll give the depth as 250 mm. Also, I'll change the direction to reversed, and the operation was add material. I'll change it to add frozen and generate. So this is the airfoil that we are going to analyze now. I'll go to XY, look at. I'll go to sketching and choose line. I'll draw a boundary here of 4 lines. Then I'll go to modify and choose trim option. I'll remove the extra lines from here. Then I'll give dimension to these lines. I'll give H1 as 200, L3 as 50, L4 is 50, V2 is 100. Now once this bounding box is made, I'll go to modeling. Here I'll go to extrude. I'll select the sketch one that I've just created. Operation is add frozen. I'll give the dimension as 250 and I'll generate. So you can see here this box is made. Now next what we have to do is give the angle of attack. So I'll go to create, body transformation, rotate. Bodies is this solid which I want to rotate. Apply. It is asking for the axis selection, that is the XY plane, and I want to give the angle as minus 10 degree. And generate. Now you can see here that the surface is still remaining, so I'll just right click here, suppress body. Also the line body is remaining, so I'll right click and suppress this body. Now once this is done, I'll go to create and select boolean. Operation is subtract. Target body is the outer one and tool body is the inner solid, and then I'll select generate. So you can see here the geometry has been created. Now I'll close this window and I'll go to mesh and double click. I'll go to mesh, element size, I'll change it to 0.01 meter and generate. So you can see here the meshing is done, but we need to refine it further. So I'll right click here and insert sizing. I'll select this airfoil area, apply. Element size, I'll give it as 0.001 meter and generate. So once you click on the mesh, you can see the refinement has been done. Now I will give the name to these ends. So I'll select this one, right click, create name selection. This is the inlet. This side is the outlet. The front and the back surface are the symmetry 1. So I'll right click, create name selection, symmetry 1. The upper and the lower surface, I'll rename them. I'll say wall. Now you can see here, this is the inlet outlet, symmetry 1 and wall. So once you have created all this, just go to mesh once again and update. You will read a message here that the mesh translation to the fluid was successful. So now this window can be closed. We can go to setup and double click here. Here I'll choose double precision, solver processes are 2 and start. First we'll go to model. The viscous model SST-K omega has been selected, so I'll leave it as it is. Material for fluid, it is air, so no need to change it. Here you can see that by default we have chosen pressure based, velocity formulation is absolute and time is steady. So next you should go to boundary conditions, inlet, double click on inlet velocity. The value of velocity magnitude I'll give as 15 meters per second, apply and close this. Next I'll go to reference values, compute from inlet, reference zone is a solid. Next I'll go to methods. Here you can select second order upwind in the turbulent kinetic energy model. So this is by default, and if it is not, you can just change it. Then I'll go to monitors, report plots. I'll click on new and then again on new. Force report, drag. Here I'll write down drag CD. And here I'm going to choose the all solid. And here I'll select print to console. OK. Again I'll click on new, force report, lift. This name I'll change it to lift CL. I'll select print to console, wall solid, OK. I'll click on OK now and then close. Next I'll go to initialization and double click. Hybrid initialization is chosen. I'll click on initialize. You can read here hybrid initialization is done. Then I'll go to calculation activities. Double click on autosave every iteration. Here I'll give the value as 20. OK. Next I'll go to run calculations and double click. Number of iterations I'll give as 250 and calculate. You can see here the calculation is complete. So click on OK. You can check where the solution has converged. You can see here 117 number of iterations have been calculated, and at this iteration the solution is converged. We have given 250, which is more the number. Also you can see here this is the drag plot. Now you can see that the maximum drag obtained is 0.0029 and the lift that you can see is actually negative. You can see here these values are negative. The reason is because we have given a negative angle of attack. If you look at this geometry, you will see that the aeroplane is actually moving downwards. It is trying to come to a halt, or it is trying to reduce the velocity, hence it is in the downward direction. So this is what you can see over here. Now we will close this window. Okay. We'll come to the screen and double click on results. Now in results, we'll first go to streamline. Okay. We'll start from symmetry 1. Number of points I'll give as say 50. Apply. You can see here, this is how the streamline flows over the aerofoil. Now we'll go to animation. We'll shift to sweep animation. We'll select streamline 1. Remove the forever loop and give 3 loops and then play. So now you can see how the flow will take place over the aerofoil. Now the size of these particles are a little larger, so we can change that. We'll go to options. Here we have selected the symbol as ball. So the symbol size, I'll give it as 0.5. Okay. And we can again play. So now you can see the particle size is smaller. Now you can see the velocity is higher in this zone and here it is lesser. I will close this. We'll remove the tick from here and we'll click on contour. Okay. We'll change the range to local. We are creating for pressure. Location is symmetry 1. Number of contours I'll give as 100. These are the contour points. And then I'll go to render and remove show contour lines and click on apply. So now you can see that the pressure is higher in this zone and here it is lesser. The highest pressure value is 164.675 Pascal and the lowest value is minus 474.49 Pascal because the velocity was higher in the lower zone. So next we will go to contour again, remove this contour 1 option and click on contour 2. I'll change the location to symmetry 1, variable is velocity, range is local and number of points I'll give as 100. I'll go to render and remove show contour lines and click on apply. Now you can see that the velocity is higher here. The highest value is 28.4 meters per second and in these zones it is lesser. It is just 0 in these zones. So here you can analyze the velocity profile over the aerofoil. So with the use of CFD Fluent, you can actually calculate the pressure profile and the velocity profile over the aerofoil. So with this, I end the session. I hope you have understood the analysis. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.